So you've had a day to work on implicitly defined functions and to work on them in your groups. And so now we're just going to take this and flesh it out a little bit more to the next level. We're going to go to higher order derivatives. So same idea, but we're going to take it to second derivatives. Okay, so where we could find not just the first, meaning velocity, but we could also find the second, which would help us do the acceleration of some of these functions. So let's take a look at that. All right, so this notation, as you remember, okay, that's the notation for finding the second derivative. Again, this is Leibniz's notation. So in order to get to the second, we've got to do the first derivative. So we'll do a DCFS to find the first derivative of this. By the way, just incidentally, it's not important, it's not essential to the understanding of this, but this shape is a circle, okay? So clearly this circle, a circle would fail the vertical line test, but something that was following the shape of a circle would certainly have velocity, and it would also have acceleration as well. All right, so the DCFS. All right, and remember we're talking about the implied parentheses. So our first derivative would be 2 parentheses x to the first times dx. And then 2 parentheses y to the first times dy dx, and then equals the derivative of 25, which is 0. And then we will want to reduce and clean up what we've got. So we're looking at 2x plus 2y times dy dx, and then equal to 0. So this is a nice straightforward equation. So we've done our differentiate. Now we're going to collect, and there's only one dy dx term, so I'll kick the 2x to the other side, so negative 2x. So I've collected everything on the one side. There's no need to factor because I only have one of those terms, but I can solve by dividing. So dy dx would be equal to negative 2x divided by 2y, which reduces to negative x over y. All right, that's our first derivative. What we want to do now is move on to find the second derivative. All right, so now we're ready to find the second derivative. All right, what we're going to find is the derivative of what we just had. And in order to find that derivative, we are going to need the quotient rule because the result was a quotient. So we'll tackle this just like we would any quotient rule. So I start with y, and I do the derivative of the numerator, which would be negative, and this will be dx over dx. I'll just caution you, please don't make that a -1 right now. Make it a dx over dx so we can see how this is all going to work together. Minus, and then my numerator is negative x, and the derivative there would be then positive dy dx over y quantity squared. All right, so now we look back and we see what we can simplify and what we can reduce. So I notice that this dx here is going to simplify to 1. And then the dy dx also simplifies, and this is one thing that people maybe neglect. The dy dx simplifies to something else. Okay, well, we just figured out what dy dx was. So this dy dx simplifies to negative x over y, which was the result. That's always going to happen when you're working with the second derivative. You should be at some point plugging in what you got for the first derivative. It will always happen that way. All right, let's clean this up and take a look at what the result is. So my first term ends up to be y times -1, or negative y. And then looking at all the negative signs, I've got 1, 2, 3 of them, negative signs, so this will be negative, and then x squared over y, and then the denominator is y squared. All right, now this can be cleaned up significantly as well. You may find that depending on where you stop, you're not going to get the same answer as the back of the book. So it is a good practice for you to work through some algebra to say, how can I simplify this more? Because this term right here, having a fraction in the numerator above another fraction, having over a different denominator, that's just not good math, okay, not good format. So how can we clear that out? Well, anytime we want to clear out denominators, we simply multiply through by a common denominator. So if I choose to multiply this term by y so that I can reduce the denominator, I'll have to multiply this term by y as well. And if I did it to both terms in the numerator, I'll need to multiply the denominator by y. So let's take a look at what we've got. This will simplify to negative y squared minus, and then by multiplying now I just have negative x squared over y to the third. And again, you might, oh, that looks a lot better than what I had, but you might check the back of the book and be like, oh shoot, well they have something different still. What else algebraically can I do? Well, I see that both terms have a negative in common, so what if I factored out a negative 1? Then I would be left with y squared plus x squared. Or if we put that in the right order, maybe it would be better to put x squared plus y squared. And then that is over the denominator of y cubed. And that looks pretty good too, but you may look in the back of the book and be like, shoot, it still doesn't match what's in the back of the book. So what else algebraically can I do? And I want you to look at this x squared plus y squared. You know, where else have we seen x squared plus y squared? Well, if you go way back to the beginning, it was our original problem. X squared plus y squared is equal to 25. It's like kind of like the Pythagorean theorem, you know, that sine squared plus cosine squared is always equal to 1. Well, in this problem, x squared plus y squared, because it's a circle, is always equal to 25. And so we can simplify this even further and say, well, this turns out to be negative 25 over y cubed. And that is the expression for the second derivative, and that is as simple as you can make it. All of these steps at the end are all not calculus steps, they're just all algebraic steps. This doesn't always happen, and it's just what I'm saying is when you look at the back of the book as your solution, if your solution doesn't yet match, it's usually because there's more algebra that you can do to make those things be equal to each other, make it match. Now, if this is a free response question, you can stop at any equivalent answer. However, it's multiple choice. You're going to have to work until you get an option that is one of the choices. All right, so let's try that one more time. All right, finding our second derivative. Well, all right, it's going to be DCFS to find the first derivative. All right, so finding all of our derivatives, let's make sure we have parentheses around what we need. And I have parentheses around one of the y's, but I need it around the x, and I should have it around this y as well. Remember, those are implied parentheses, which is where we get the word implicit differentiation from. All right, my derivative of 2y is 2, not just 2. Again, there's where people are going to make the mistake. The derivative of 2y is not 2. The derivative of 2y is 2 dy dx. Oops, equals. The derivative of x squared is 2 parentheses x to the first times the chain rule of dx dx. Plus, okay, the derivative of sine y is not just cosine y. Because cosine y has the implied parentheses, it is followed by, because of the parentheses, dy dx. Okay, always those key parts there. Now we can go back and reduce the dx dx, so we'll have 2 times dy dx, and then 2x, and then cosine y times dy dx. All right, my differentiation step is done. Now I'm going to collect and gather the like terms together. So I notice I'm going to move this term over to the other side. So I'll have 2 dy dx minus cosine y times dy dx, and then equal to just the 2x that would be left. So I've collected all those like terms. Now I'm going to factor the dy dx out, which is 2 times the cosine of y being equal to 2x. So my factoring step is done. And then I'll solve using division. So the first derivative would be 2x over 2 minus the cosine of y. Okay, that is my first derivative. Now I'm ready for my second derivative. Once again, our second derivative is going to require us to do some quotient rule work. So we're going to start with the denominator of 2 minus cosine y and multiply that by 2 times dx dx. So the prime part should always have something with dx in it. And then minus our 2x, and then multiplying by 0 minus, plus the derivative of cosine is negative, sine y times the chain rule of dy dx. Okay, just remember the prime part, okay, low d high minus high d low, those derivative parts should always have a dx term. And then 2 minus the cosine of y, quantity squared. So now those derivative terms, okay, dx dx will get replaced with 1. dy dx will get replaced with the result for dy dx. So we'll have 2x over 2 minus cos y. So let's see if this cleans up at all. Still going to have quite a significant numerator, I think. Remember, this term right here will now just be the number 2, and it will need to get distributed as I'm simplifying my quotient rule. So I'll have 4 minus 4 cos y. And then my next term, when I combine everything and simplify it all together, I'll have minus. Okay, this 2x distributed to the 0, that's just 0. And then this is distributed to this whole term. Okay, all of this is one term here. So the 2x is multiplied by that whole quantity. So I will end up with 4x squared. That's the 2x multiplied by the 2x and the sine y as part of that, over the denominator 2 minus cos y. And then my denominator is 2 minus cos y quantity squared. All right, then, because we end up again with a fraction as a part of a fraction, we will want to multiply to help this clean up and be more simplified. So we want to take this and multiply by 2 minus cosine y as an expression. And we want to multiply this by 2 times 2 minus cosine y. And we need to multiply this by 2 minus cosine y. So this just becomes an exercise in algebra. All right, this 2 minus cosine y will reduce that 2 minus cosine y. So we will end up with Let me just shrink this down just a little bit. Four minus 4 cos y times 2 minus cos y minus the 4x squared sine y. And the denominator is now 2 minus cosine y, that whole quantity cubed. Now nothing cool happens this time like it did last time, where you end up with something identical with what you started with. You could FOIL this out if you wanted to, but I checked, and when I FOILed, nothing really remarkable or cool happened. So we can just leave it like that and not bother expanding it because it was not to our advantage. All right, so sometimes when you do, and you're again trying to match the back of the book, the algebra is helpful for you to keep simplifying, and sometimes it's not. And the back of the book is just going to have kind of a, doesn't look very attractive. It's really complex and not as elegant of a solution, but it's still the correct solution. All right, you guys are doing great work on your own here, so keep encouraging each other and supporting one another. Send me questions as you have them, and then we'll work through this together later this week. All right, thanks.